Here is an example of an ARMA 1-1 model. So consider an ARMA 1-1 model, and let's say it is xt minus 0.95 xt minus 1 equals 80 minus 0.25 80 minus 1. So naturally, just by looking at it, we will have theta 1 is 0.25 and phi 1 is 0.95. So we want to find the first full pi and psi weights of the model. So let's start with the pi weights. So we know that pi 0 is 1 and pi 1 is simply theta 1 minus phi 1. So that is just the standard derivation that we have. So pi 1 would simply be equal to the value of theta 1, which is 0.25, minus phi 1, which is 0.95. We end up getting negative 0.7. Pi 2 is, you can either use the recursive equation. We have pi 2 to be equal to theta 1 times pi 1. The general recursion is pi k equals theta 1 k raised k minus 1 times pi 1, or we could have pi k equals theta 1 times pi k minus 1. So pi 2 would simply be equal to theta 1 times the value of pi 1, and theta 1 is 0.25 times negative 0.7. So we have 0.25 times negative 0.7, which will give us negative 0.175. And pi 3 would simply be equal to theta 1 times pi 2. So that would equal 0.25 times negative 0.175. And we would end up having 0.04375. And eventually the pi's would simply become 0. They would converge to 0, which is why typically we don't want to have an infinite representation. We can truncate it at some p or q. In a similar manner, we could find the psi weights. Psi naught is equal to 1, and psi k in general is phi 1 raised k minus 1 times psi 1, or we could write it as psi k equals phi 1 times psi k minus 1. So in this case, the psi's, the first psi would be phi 1 minus theta 1. So with pi's, we had theta 1 minus phi 1. With psi's, we have phi 1 minus theta 1. So this would imply psi 2 is equal to phi 1 times psi 1, and psi 1 is simply 0.95 minus 0.25, which would equal 0.7. So psi 2 would equal 0.95 times 0.7, and that would be 0.665. In a similar manner, psi 3 would equal to 0.95 times 0.665, and which would be 0.6318. And you can see this AR part is decreasing in terms of the psi weights slowly compared to the pi weights. The pi started at 1, then moved to negative 0.7, and it dropped really fast. But the size, it's pretty gradual. That is because of the values of phi1 and theta1. Phi1 is 0.95, theta1 is 0.25, so the pi weights would approach 0 faster compared to the psi weights. So here is another example. So let's say we have an ARMA 1-1 model, and we have autocorrelations. Row 1 equals 0.85, row 2 is 0.32, and row 3 is 0.18. And our objective here is to find the model. How would we go about doing this? We know an ARMA 1-1 model is xt times 1 minus phi1 times b equals at times 1 minus theta1 times b. We'd like to find the value of phi1, we'd like to find the value of theta1. So we're going to estimate these values using either the pi weights or the psi weights. Oftentimes it is easier to use the pi weights rather than the psi weights, because estimating moving average processes are typically more involved than estimating autoregressive models. So I'm going to make use of the pi weight. So what we know is we could write AT as sum j equals 0 to infinity pi j times x t minus j. In other words, that would simply equal to pi naught xt, pi 1 xt minus 1, pi 2 xt minus 2, pi 3 xt minus 3, and so on. So pi naught is simply 1, pi 1, we don't know what that is, pi 2, we don't have an idea, pi 3, we don't have an idea, but what we know is the autocorrelations, and we can estimate the model using those autocorrelations. But before we can do that, we should realize that I could write it as negative phi1 prime xt minus 1, negative phi2 prime xt minus 2, negative phi3 prime xt minus 3, and so on. So where we have phi1 prime is equal to negative pi 1, phi2 prime is negative pi 2, phi3 prime is negative pi 3, and so on. Now, if you look at the model that we have, here, that is an AR model. Even though it is AR infinity, in other words, it has infinite terms, in order to estimate an AR MA11, we simply need two equations. And how do I come up with that two? It is simply P plus Q. P is 1, Q is 1, so we end up getting 2. In other words, we don't want to go beyond phi2 prime, so I can just stop at phi2 prime. So I'm going to treat the infinite model that I have as simply an AR2 model. And I'm going to estimate phi1 prime and phi2 prime using the autocorrelations. So if we use Yule-Walker estimation, we have rho 1, rho 2 equals 1, rho 1, rho 1, 1, phi1 prime and phi2 prime. And I'm writing it as phi1 prime and phi2 prime because it is for the model that we rewrote as an infinite AR model. Rho 1 is given in the problem, which is 0.85. Rho 2 is 0.32. And our goal is to estimate the value of phi1 prime and phi2 prime. So let's define some matrices here. I'm going to define matrix A. And I'm going to define matrix B. Now to find phi1 prime and phi2 prime, all I have to do is find B inverse A. That's odd. I didn't expect that to happen. Let me check here. Ah, that has to be 1. And I end up getting 2.083 and negative 1.45. Mind you, these are not the theta 1 and phi 1 in the ARMA 1-1 model. These are just the coefficients for the model that we rewrote. So we have to go back and realize that phi 1 is minus phi 1 prime, pi 1 is minus phi 1 prime, and pi 2 is minus phi 2 prime. We know that pi 1 is simply phi 1 minus theta 1. Have it backwards. And note the theta and the phi here correspond to the original ARMA 1-1 model, which is right here. So, which is right here. So, theta 1 minus phi 1 would equal minus 2.083. And we know pi 2 is equal to theta 1 raised 2 minus 1 times pi 1. Which is simply pi 2 equals theta 1 times pi 1. Now, I already know what pi 1 and pi 2 are. Pi 2 is negative of negative 1.45 because pi 2 is negative phi 2 prime, and theta 1 times pi 1 is negative phi 1 prime, so I have minus 2.083, which would imply theta 1 is 1.45 divided by 2.083. And that would give me 0.6961 for theta 1. Now going back to pi 1 is equal to theta 1 minus phi 1, and that equals negative 2.083, which would imply 0.6961 minus phi 1 equals negative 2.083, minus phi 1 would equal to negative 2.083 minus 0.6961. So minus phi 1 would equal to 2.083 plus 0.6961, which is 2.7791. So phi 1 would be negative 2.7791. So what we have here is xt times 1 minus phi 1b equals at times 1 minus theta 1b. We found the values of phi 1 and theta 1, so we have 1 minus of minus 2.779 times b equals at times 1 minus 0.6961b. So xt times 1 plus 2.78b would equal at minus, or 1 minus 0.6961b. If we distribute the xt and the at, we have xt plus 2.78 xt minus 1 equals at minus 0.6961 at minus 1. We have to make an important note here that this model that we estimated is invertible, but it is not stationary. The reason because theta 1 is 0.6961, it's definitely less than 1, and theta 2, phi 1 is negative 2.78, which is less than minus 1. And we want the value of theta 1 and phi 1 to be between negative 1 and 1. So that checks out for invertibility, but that doesn't work out for stationarity. Oftentimes, when we do Yule-Walker estimation, it so happens that the model that we estimate may not be stationary. It is a common thing that happens, which is why we have other estimation techniques such as Berg's estimation and innovations algorithm and so forth. But the easiest one is a preliminary estimate that we obtain using Yule-Walker equations.